quite 5 minutes, but we'll keep on moving along here. So Veronica did a very good job of covering some basic hydrology concepts. In the past, Veronica and I have been called lots of things. Specific to our jobs, actually, hydrologists, hydrologic engineers, et cetera, et cetera. There are professional hydrologists. Some of them work for NOAA, USGS, probably do private consulting and whatnot. And they give us the design flows, right? Our hydrographs, our peak flows, our low flows, if you're doing something related to aquatic organism passage and other types of things, working in wetlands, that type of stuff. We are actually hydraulic engineers, so we do some of the flow stuff. We can't claim that we are die-hard experts in everything dealing with hydrology, because that in itself is a profession. But we do come up with our flow values, our capital Qs, and then the fun stuff for us really begins, because then we take that and then we determine velocities, depths, shear stresses, and how those impact our transportation infrastructure and our natural environments, our ecosystems, and then we use that information to inform our design, and then we collaborate with the structural engineers, the geotechnical engineers, the roadway designers, and other types of disciplines to actually come up with the infrastructure designs. So Veronica covered the capital Q stuff, and now we're going to go into, well, what do you do with some of that capital Q stuff for your design? And that's what we're going to talk about in these next several lessons, and actually continuing on into tomorrow. So for this afternoon, we're going to cover some very basic hydraulics terminology, and we're hoping that this is in large part a review for you. But it's always a good idea to cover some common ground to make sure we're all at the same level. Once we cover some of the basic hydraulic concepts and terminology and different types of flow and the way we describe flow that occurs in our projects and in nature, then we're actually going to talk a little bit about, well, how do you use that to maybe design some open channel flow type things, like your roadside ditches. After we cover that, then we're going to do a brief lesson on weirs and orifices. And I actually looked this up. There is no such thing as orify. It's easier to say. It maybe sounds kind of strange, but it's one less syllable, and for me it's easier to say orify than orifices. So maybe you have a preference, choose either, and I certainly won't say that. So the reason we're covering all these things is they're critical in design. So even when we get into weirs and orifices, you have to think, why is this important? And it will become readily important first thing tomorrow morning when we start getting into one of my passions, culvert design. All right? It's all good stuff. So with that, let's launch. So, learning objectives. So these are the things we're going to talk about. We're going to describe the types of flow in open channels. We have lots of different ways of describing things. And depending on what your design situation is, some of them are more important than others. But we're going to try to talk about different ways we describe them. And ways we use to describe flow also include these terms subcritical and supercritical flow that relate to the fruit number. One of the big design equations we use in very specific circumstances is Manny's equation. We're going to talk about Manny's equation, and Veronica already introduced it. And then we're going to look a little bit more at applications of Manny's equation and where it's appropriate to use it and where it's not appropriate to use it. We're going to then talk about 3 fundamental equations in hydraulics, and if you had to take a guess at what those are, 3 big ones. You always hear about them in kind of like the same sentence or the same discussion. Say again.
Manny's equation?
Manny's equation is not one of the big 3. It's one of the ones that we use. Continuity, energy, and momentum. Exactly. Those are the big 3. And then we're going to do a couple of really quick practice problems using conservation of energy and conservation of mass. to solve a couple practical problems. So resources. So one of the key things coming out of this, and one of your key takeaways, if you want more information on anything that we talk about during this week, where can I go to get that information? The primary source is the Federal Highway Hydraulic Engineering website. And if you're one of those folks who has trouble remembering all of the web links until you have it listed as one of your favorites, I'll do what I do. I'm not actually supposed to say Google it. I think I'm supposed to use more general terminology because all of us government employees can't market proprietary things. But I always use Google. I find it to be the best web search engine, to be honest. So if you ever wonder about any of these resources, HDS4, you can go into Google and type in HDS4 and it should point you in the direction of our website. Okay, so we have lots of goodies up there. I think you were watching some of Jim's YouTube videos on culvert concepts, open channel flow concepts, inlet breaks, and other types of things. We continue to develop more videos, so stay tuned for those. We have I think 3 different projects in the works with more hydraulics related YouTube videos. I like the free stuff, so all of our videos are free. And I also want to plug our free web-based training through NHI. So if you go onto the NHI website, you're going to find several web-based training courses. And I think a couple of those were prerequisites for this week. The one that you probably have not taken to this point is the Hydraulic Toolbox. And we're going to talk about the Hydraulic Toolbox as one of the free software programs from Federal Highway Administration, and the utility of it and what you may be able to use it for on your projects. One of the key documents for all stuff introductory in hydraulic engineering is Hydraulic Design Series 4, Introduction to Highway Hydraulics. So we actually have an Introduction to Highway Hydraulics NHI course, and we're kind of doing some semblance of that this week. It's not exactly the same, but we pulled some material from that course. The reference document for that course is HDS4, and so if you want to review any of the concepts we've talked about this week, we recommend going to HDS4. It's a pretty easy read, and as you will become aware here very shortly, a lot of the practice problems that we're doing here are actually solved with the solutions in HDS4. So if you wonder where some of the numbers came from and some of the practice problems we're going to do, you can just go back to HDS4 and it will lead you right through the process. Drainage design, we talked about it. We take our flows, our Qs, and then we calculate certain things. Some of the key parameters we're typically interested in: velocity, flow depth, shear stress, and those sorts of things. And we primarily deal with, well, as roadway designers, you're primarily dealing with open channel flow. So you have a free surface that's exposed to atmospheric pressure, or you have also free surface flow in a conduit. So when you design your storm drains and for gravity flow situations, then they will have a free surface in the storm drain itself. Every once in a while we get into pressure flow. We'll talk tomorrow about outlet control culverts, and they flow in either a subcritical mode or a full flow mode. If they're flowing full, then they're in pressure flow. But we don't deal a lot with pressure flow in our careers. That's more water supply and distribution type stuff. And if you get into pump stations, then of course you have pressure flow situations too. All right. One key way we describe flow. Remember, this is one of our learning outcomes. Uniform, non-uniform, and then gradually varied. So uniform flow, and it's kind of right down here on the bottom of your slide. The depth and velocity are fairly constant with distance. Distance down your ditch line, distance down your open channel, distance through your culvert. If you have depth and velocity maintaining themselves in a fairly uniform fashion with distance, uniform flow. If your depths and your velocities vary with distance, then of course, we try to keep things simple. It's non-uniform flow. Uniform flow in reality is very rare. Even with a prismatic or a trapezoidal ditch line channel, you're going to have variations, right? You're going to have rocks in there, or a tree trunk or something. So you may have dips and bumps and things. So in reality, uniform flow is rare. We can get that in the laboratory through running water through a flume. In a lot of cases, we can get almost close to uniform flow. So actually, in reality, we look more towards very gradually varied flow is probably more realistic, where you have some variations in depth and velocity with distance, but they're not to the degree where it's non-uniform. And we're going to look at examples of these in a series of pictures coming up. So that's varying with distance. So when you talk about uniform, non-uniform flow, automatically think about distance. And are things changing with distance? Conversely, we also can describe flow as steady and unsteady. And when you hear steady and unsteady, think about time. So you're not thinking about distance now, you're thinking about time. And if you're standing on your riverbank and you're looking across to the channel to the other bank over there, is the water surface going up and down with time? So that's changing depth and velocity. And if it is, that's unsteady flow. If it's fairly consistent with time, maybe it hasn't rained in a while and you just have your normal base flow, your groundwater's feeding the flow in your channel, and it's fairly steady over the course of hours and days, that's again steady flow. So uniform, non-uniform is distance, steady, unsteady is a time component, a time indication. All right, now into the good ones, subcritical and supercritical flow. So some of you have heard of these terms before. The way we tend to envision these things is water approaching and then going over a dam or spillway. So this is actually kind of like an OG spillway shape here. So on the upstream side, where maybe you have some backwater, so the water has built up and raised in elevation going up to and approaching this OG spillway, you may describe this flow as deep, more tranquil, slower moving. And so when you hear those types of terms, you're going to think, well, that sounds to me like a description of subcritical flow. And then the fun begins. It approaches the crest of the spillway, it breaks through a control section. And when you hear control section in these next couple of days, think critical depth. So a control section is a point where we can actually calculate the exact depth of flow there. So our control section here is critical depth. So we have subcritical, this is deeper, tranquil flow approaching the OG spillway. And then it goes over here and it's like a water slide shooting down here. So it goes from subcritical to supercritical flow. So terms that are somewhat synonymous and descriptive of supercritical flow: shallow, rapid, high velocity, lots of kinetic energy. When you hear those terms, think of supercritical flow. Lots of kinetic energy in supercritical flow, lots of potential energy in subcritical flow. And then when you have that transition between the two, that's going to be, when you go from sub to super, that's going to be going through critical depth, your control section. How do you actually calculate? If you wanted to calculate whether a flow is sub or supercritical, well, one good way to do that is with our good friend, the Froude number. So the Froude number is V over the square root of GY. Okay? What's V? That's the flow velocity. That's your average flow velocity. You can come up with an estimate of that. The square root of GY is called celerity, or it's the velocity of, this is going to sound like mumbo jumbo, but it's the velocity of a shallow gravity wave. So what does that mean? So you go out to a lake, you have your nice big rock, and you put that rock into the water, and then you see that wave spread out. The velocity that wave spreads out is the celerity. So what does this mean? So it's a ratio of these two, and then you calculate a Froude number. So you take the average cross-sectional velocity to celerity, and you calculate a number. If this number is larger than 1, this means that your flow velocity is larger than the celerity of that wave, which means that if you actually tried to generate a shallow gravity wave by putting that rock into a stream that's fairly fast moving, that wave will be washed downstream. So anything upstream doesn't even notice that you threw a rock in there. The wave is just washed downstream, which indicates a higher velocity and what type of flow? Higher velocity. Supercritical flow. Supercritical flow has Froude numbers greater than 1. Conversely, if you go out to that lake and you have this nice slow tributary coming into your lake, okay? So this nice slow moving stream or whatever, and it's just kind of easing in there, and if you throw that rock in, it'll propagate downstream for sure, and some of that wave will propagate upstream. So it will move upstream because the velocity of that flow is less than the velocity of that shallow wave. So it moves upstream. Slower moving velocity, Froude numbers less than 1, subcritical flow. Froude number less than 1, subcritical flow. And then in between the two, where you have a Froude number exactly equal to 1, we say we're going to calculate this critical depth. In reality, there are places that you find critical depth, but it's at a point. Like when we had that OG spillway, there's one point over the top of that spillway where you have critical depth. So you're not going to have it over an extended reach length or a ditch line or stream or whatever. It's typically at a point, and it's a transition from sub to supercritical flow. You can actually calculate critical depth. Here's a general equation for it. Your flow associated with critical depth squared divided by the acceleration of gravity, the area of the flow associated with critical depth, the top width of the water. Whenever you see T, capital T in hydraulics, that typically indicates the top width of your flow. So here's a general equation, and then you can turn this into how do you calculate critical depth for a rectangle. Other shapes other than a rectangle becomes a lot more complicated. Like if you're trying to calculate critical depth of flow in a culvert, a circular section, it becomes pretty complicated. And so what they have done is they've developed charts to actually, you go in with your flow and you can look up the critical depth in a pipe. And I think they've done other shapes. We don't care because we just figure that out in the hydraulic toolbox. So we don't calculate it by hand, actually. All right, so if you calculate critical depth and say it's like a foot, so whatever, and it's dependent on your cross-sectional shape. Say we calculate this hypothetical critical depth and it's a foot. If we have water that's deeper than critical depth, then what type of flow would you say that is? Deeper. It's subcritical depth. It's deeper flow, that's subcritical flow. If you calculate, or if you have a flow depth of half a foot, it's shallower, it's less than critical depth. That flow would be described as supercritical. Okay? See how this is kind of all coming together? All right, so again, if I personally were to describe the supercritical flow to someone, I would say, you know what, it's kind of like shallow, it's rapid. If you've done whitewater rafting, kind of like bubbly, white watery, the Froude number is greater than 1, the depth is less than critical depth. These are all indications of supercritical flow. Vice versa. Subcritical flow. Well, you know, it's deeper, it's more tranquil. Picture yourself maybe in a pond or a lake or whatnot. That's really subcritical flow, but you're getting the idea. The true number's less than 1. The depth is greater than critical depth. Those are all indications of subcritical flow. It just sounds kind of mellow, right? Subcritical flow.
And why is the hydraulic depth correct? Or
Oh, I'm sorry, why is just the flow depth?
but,
Technically, I mean, we use hydraulic depth in open channels. I mean, yeah, so, but we're just trying to keep things a little bit more general, so we're just saying flow depth, comparing that to our critical depth. All right, so once again, this OG spillway, and you'll see this again tomorrow when we talk about culverts. Sub, super, control section. When you hear control section, these next couple of days, think, where's critical depth? It's at the control section. All right, so if you watched those YouTube videos, I think Jim actually demonstrated a, what is this?
hydraulic depth.
It's a hydraulic jump, exactly. And what you have here is this shallow, fast-moving flow, supercritical flow. And then all of a sudden you come into a situation where you have high tailwater or high downstream water level. And the momentum of this is smashing into this, and it's jumping up into subcritical, the deeper, slower moving flow, subcritical flow. And that transition, and it only goes this direction for hydraulic jump. That's the transition from supercritical to subcritical. All right, so let's practice. If you were to look at this and describe the flow and the different types of categories that we just talked about, how would you describe this?
Super.
Okay, so I'm hearing on the left, it looks like it's subcritical. It looks like it's deeper. It looks like it's a little bit more mellow. I can buy that. And then what do you see over here?
Supercritical.
Yeah, it looks like supercritical. You see kind of like the white water. It's got lots of turbulence and whatnot. That's definitely supercritical. Okay, so this is a question I have, and I think I know the answer, but I'm not 100% sure which direction you think the flow's going.
Towards the right.
To the right. Okay, why do you think it's going to the right?
It's like, because suddenly.
Because if it's lower, you can't get it so
Sub
high.
is a super.
Because it's crashing and everything.
Branches along the shore are pointing my way.
Yeah.
You know, I think, actually, I was looking at that as one of the indicators, and I think you're exactly right. You think this might be weighed down by like a root bowl or something that's kind of like stuck in the water, and then eventually this kind of like maybe turned this direction because the flow's moving that way. That's what I was thinking as one indicator. What else? I mean, could this be a hydraulic jump? In which case, water would have to be going this direction, right? And I thought about that, and it's like, you know, there's a pretty good demarcation line here. So I'm thinking if you see a hydraulic jump, it's kind of roiling and bubbling, and you would still see that occurring over a length here. And so that's why I'm kind of thinking apart from this, the tree branch is pointing this way. I'm kind of thinking that water's cascading over here, and then just kind of like doing some sort of funky turbulent circulation pattern. So that's one of the things that we kind of do as hydraulic engineers is we try to do some forensics and try to figure out what's going on and what's going on and what the flow is doing. And that's kind of one of the neat things that we like to look at. Okay, so you described this in sub and supercritical terms, but we talked about other ways to describe flow. So what else is going on here? How else would you describe it? Yeah, well,
It's open channel.
okay, perfect. Who said that? Non-uniform. Yes, Chris is a winner. He said non-uniform, right? Because we are seeing here that depth and velocity are indeed varying with distance. So this is non-uniform flow. What about steady, unsteady? Yeah, I mean, to actually get a good indication, I mean, you will see this probably bubbling around a little bit. But what we would really want to be looking for is there like this significant raising and lowering of the water surface. Who knows? Looks kind of like a nice sunny day there. Maybe things are fairly stationary. It might be kind of steady. I really don't know. What about this one?
It's definitely steady.
Right on the road.
Hopefully this isn't one of, this is Missouri. Yeah, I thought I had some Missouri photos. Does anyone even this is probably a long shot. Does anyone recognize this location?
That's
Probably not.
Sexton.
I was just gonna say, you probably see a lot of this stuff. So how would you describe it?
Subcritical.
Yeah, you know what? I'm thinking it's kind of slow moving. It looks like, well, it's at flood stage or it's receding from flood stage, so it's probably deep. So I would say it's probably subcritical flow, except for maybe the flow that's sheeting over the roadway. What else?
Steady.
Okay, so steady versus unsteady. Which one did you say?
Oh, steady.
Yeah, unsteady because it's a flood hydrograph, right? It came up to a certain level, and at some point it's going to start receding. So if you stood here long enough, you would see a raising and lowering of unsteady flow. Uniform, non-uniform. Yeah, it's probably doing all kinds of things, going over the road, and it's probably going out laterally at different points in the floodplain. Going out, coming back in, so I would say it's probably non-uniform. All right, if there's water in this one, what would you describe? How would you describe it? Let's not worry about sub and supercritical at this point, but how would you categorize it as far as uniform, non-uniform, and steady, unsteady?
Right, I mean, steady as you go.
Yeah, I would say it's, I heard gradually varied, which is probably technically correct, but in most cases, we would just assume it's uniform flow, right? And then if you were actually designing this and you had your design discharge, then we would just consider it steady flow condition, steady uniform flow. So here is one that I think would definitely be more gradually varied with distance. And then again, if you're choosing a peak discharge to design your median swales and your roadside ditches, then we would say a steady flow condition. If you took those wattles out, it would be more like a uniform flow condition. Okay. This one?
Steady and uniform.
As far as sub and supercritical, I think it's, I don't know visually that I could honestly tell. I mean, you see some roiling of the water surface, but you can still have that with subcritical flow. A lot of our bridges, unless they're in mountainy terrain, tend to be subcritical. That's not always the case, but there's a tendency for subcritical flow. But I don't know that we can actually tell from this photo. It looks to be, to me, if it's not raining, if there's not a storm going on, or if it's not receding from a storm event, it's probably fairly steady and uniform. Again, in natural rivers and streams, they're not typically uniform flow conditions.
Well, then you got natural conditions on both sides, and then you got that bridge kind of constricting it, right?
That's a great
Head
point.
walls and everything.
And so we have a equal-made structure here, and so you have flow contracting through, so it's coming in from the side and it's kind of contracting through the opening. And so just even from that perspective, that's a great point. It's not going to be a uniform flow condition. All right, great. Why did we go through all of that? Well, we have our good friend Manny's equation that Veronica introduced to us this morning. She showed it as the original form with the velocity times your unit conversion for US customer units over the Manning's roughness coefficient times the hydraulic radius to the 2/3. Whenever you see S in a hydraulic related equation, it's actually the energy slope. But if we have steady uniform flow conditions, the energy slope is the same as channel slope, right? And so what we see here is we use Manning's equation only for steady uniform flow conditions. And a lot of those pictures we looked at and a lot of things we discussed were not steady uniform flow conditions. So the key takeaway is be very careful where you're using Manning's equation. Because with Manning's equation, if you know the flow rate, and if you have a fancy tool like the hydraulic toolbox, or maybe you have something that was developed in-house here, then you can calculate your flow depths and your average flow velocities. So it's a powerful equation, but it's only good for steady uniform flow conditions. If you do not have steady uniform flow conditions, you may be misapplying Manny's equation. So again, capital Q is our flow rate, and we went from V over here and without an A, and then we just applied continuity, Q equals AV, and so we come up with Q times this, and then we inserted area on this side. And Veronica already talked about the hydraulic radius. We'll go over this stuff again, the wetted perimeter and the slope. All right, so that's Manning's equation. And then the three big equations that we typically talk about in hydraulic design: continuity equation, which is mass conservation; the energy equation, which of course is energy conservation; and the momentum equation, which is the conservation of momentum. Continuity, Q equals AV. Seems very simple, but we use it all the time, and it comes in really handy. So assuming that our flow rate is steady, and we have a certain velocity and area at one point in our ditch or our channel, at another point in that ditch or channel, if the area goes up, the velocity has to go down. If the velocity goes up, then the flow area has gone down, right? For the same Q. Energy equation. Is there anyone who has not seen the energy equation? Maybe it's been a while. That's perfectly fine. I'm not familiar with the energy equation. Right, so there are key components, and they're put in terms of head. And this is the velocity head, pressure head, and elevation head. Very powerful. It seems like a very simple concept, but again, it's a very powerful equation. And we say if we're at one point in our channel and then we go downstream in our channel, we have the same total amount of energy, which is made up of velocity head. But the only difference is there have been head losses in between where I'm standing upstream and then the downstream point. In open channel flow, we always lose energy as we go in the downstream direction. We always lose energy. And so if we want to say these two sides are equal, then we're adding at the downstream section the head losses back in. They're two basic components of head loss. And it's the same kind of a concept for open channel flow, for conduit flow. We have head loss due to roughness and friction. We have frictional resistance along our boundary. And so we're losing energy due to that frictional resistance. And then we have another component we used to call minor losses, but preferred term nowadays is local losses. And that's as flow is contracting, like going through a bridge or culvert opening. As that flow re-expands on the other side, as the flow goes through like bends and elbows and fittings in water distribution systems. So we have these local losses as the flow is doing certain things to move from the upstream point to the downstream point. Okay, so those are the two basic components of head loss. All right, so the key here is in conduits and pressure flow, it's actually the pressure of the fluid divided by the specific weight of whatever fluid you're putting that in terms of, and typically it's water, but it can be other types of fluid with other specific weights. The neat thing about open channel flow is your pressure term is just the fluid. So in open channel flow, your pressure head is the fluid. Momentum equation, that's just saying the sum of the forces on the system in a given direction is equal to the change in momentum. And the way you start to really wrap your head around that is to look at a couple of example problems, and they have a good one in HDS 4. They have a pipe, I think, that has a bend in it, and you're supposed to find out the forces on that bend. So where momentum comes into play, and I have it written down here, where you have rapid acceleration and deceleration of flow, flow changing and going in multiple directions, when you need to calculate forces imparted on flow or as a result of flowing water, that's when you start to get into the use of the momentum equation. So as far as modeling goes, and we're going to talk about this on Thursday morning, something like HEC-RAS 1D, it basically uses the energy equation and conservation of mass, and it does what we call standard step backwater calculations. And that's pretty much the nuts and bolts of HEC-RAS 1D, that hydraulic model. Whereas a more sophisticated two-dimensional model, and we're going to talk about a little bit about SRH 2D on Thursday, but there are two flows in other 2D model. HEC-RAS now has a 2D version to it. Those models will use conservation of mass and conservation of momentum for their solutions, because they look at flow and velocities in a plane, so it can go in all directions in a plane. So some other key terms associated with the energy equation. So this is a little bit out of sequence. I should have put this right after the energy equation. The hydraulic grade line is made up of two components of the energy, and those are, okay, so the hydraulic grade line does not have the velocity head in it. It has the elevation head and the pressure head. The neat thing again about open channel flow is the hydraulic grade line coincides with the water surface. That's exactly right. The energy grade line is all three components. It's the velocity head, pressure head, elevation head. So it's above the water surface. It can be if you have, okay, so here's where we can start tying things together. If you have subcritical flow, the velocity head or the velocity, the energy grade line and the hydraulic grade line are pretty close. Exactly. So the velocity head in subcritical flow is fairly low. So the energy grade line and the hydraulic grade line are going to be pretty close together. The energy grade line will still be above it, but not by very much. Vice versa. In supercritical flow, you would expect to see more separation between the hydraulic grade line, which is the water surface, and the energy grade line, because you have more velocity head, and the velocity head is that difference between the hydraulic grade line and the energy grade line. And so we have a couple of schematics here, and I probably should just have these up here. If this separation is a lot, you may start to suspect that that is supercritical flow, because this velocity head is pretty substantial. If these are squished together, you might suspect that that's subcritical flow, because the velocity head and therefore the velocity are pretty low. Does that make sense? So again, this is just to illustrate that, here's our total energy. The total energy at point 1 upstream is equal to the total energy at point 2 downstream, plus the head losses between those 2 points. And again, those head losses come from frictional resistance, which is the major form of head loss in open channel flow, and then local losses as you encounter flow going around bends and contracting and re-expanding and doing those sorts of things. And then here's just the difference, again, in pressure flow. It's no longer the water surface, it's the hydraulic grade line, it's the actual pressure of the fluid. And you put it in terms of feet by dividing by the specific weight of the fluid.
Well,
He is welding.
oh, you're in the pipe.
All right. Does that kind of make sense? Does it seem like it's review, or is some of this kind of new? And we'll be discussing, again, we're going over this because it's all important to doing our hydraulic calculations. So that's why we're spending time on this.